In this video, I'm going to simulate a phase lock loop using VSS, which stands for Visual System Simulator. It's part of the NI AWR design environment. I have a new project opened here. The goal of this video is to explore some of the basic properties of phase lock loops. Now, this is the reference that I highly recommend reading. Here's the title and the author for a good introduction to phase lock loops. Here on page 6, we are presented with the topology of your basic phase lock loop. So the system contains a phase detector, a loop filter, and a voltage controlled oscillator. The output of the VCO, voltage controlled oscillator, is being fed back into the phase detector. X of t is your input. It's in AC waveform with a frequency and a phase, so it's a single tone. And Y of t ideally would also be a single tone, an AC waveform, and the frequency of the output would equal the frequency of the input. So in that case, we would say the frequency of the output would be locked to that of the input. And in many situations, you also want to lock the phase of the output to the input, or at least have a fixed phase relationship between the output and the input. So back to our project. Make sure the project tab is highlighted, and then right-click on System Diagrams, click on New System Diagram. We'll call this PLL. And then this opens up our design space. Click on Elements tab down here. Click on the PLL icon, expand, VCO, there's our voltage controlled oscillator. We're going to construct our phase detector using a multiplier. So here's Math Tools, the multiplier, bring that in there, and then we need our low pass filter. We'll use a low pass Butterworth. Connect, like so. Connect the output of the VCO to the input of your phase detector. We need our reference signal, so we need a sinusoid, so sinusoid source, connect. And now our output is going to be right here. Let's put test points at the points in this network where we want to look at the signals. So test point, let's put one on the output, that makes sense. The input makes sense. Let's put a test point right here at this node, which is the signal that's being fed into the input of the VCO. So this is the control voltage for the VCO, but it's also the error signal. So this signal is going to be proportional to the error, the phase error between the output and the input. And now we need to set the type of data that each of these signal processing blocks should be processing. So to do that, you click on these arrows, double click, and click on real data. The arrow will turn from white to yellow in color. Now, I've already simulated this phase lock loop to prepare for this video, and I can tell you that you're going to get an error unless you put a delay in this feedback loop. So I'm going to do that to save us from having to look at an error message. Signal processing, delay underscore simp, click. I'm hitting Control R to rotate and rotate it in the proper orientation, and now connect the output to the input and the output to this input. Delay leave is 1, that's fine, but set this data type by clicking on the arrow to real data. Okay, now we have a bunch of parameters that we need to set here. So let's look at the input signal. The frequency we want to be 1 megahertz. Let's make this a variable, Fn. The phase, we'll make this phase in. Here's equation. Let's set Fn to be 1 e to the 6, 1 megahertz. Equation again. Phase in equals 0 radians. This Fp is the cutoff frequency of the filter, so I'm going to go F sub C. Equation. Let's set the cutoff frequency to be half a megahertz, so 500 kilohertz. For a VCO, FRQ is the free running frequency of the VCO. That would be the frequency that the output signal would have if there is 0 volts controlling this thing. So if you have no control voltage, then you would have a tone oscillating at this frequency, which is called the free running frequency of the VCO. Let's set that as 1 megahertz. Power, let's just set that at 6 dBm. leave that. KV is an important parameter. It's the gain of the VCO. It's the voltage to frequency transfer coefficient, gain of the VCO. Let's set this to be 0.5 e to the 6. So the units of this guy are in hertz per volt. If you were ever wondering, what these parameters mean, you can double click on an element and then click down on an element help, and it will tell you all the different parameters. So that's KV, what we just changed. That's the frequency voltage transfer coefficient. It's a scalar in hertz per volt. Actually, let's make that a parameter too. So let's click off this and go K underscore VCO. Make an equation for that. This way it's easy to identify this as a parameter. So 0.5 e to the 6. Let's put all of these variables over here. So when I say variables, I mean we're going to change these variables and see how the dynamics of the phase lock loop change. This is in red, so there's something wrong here. Okay, I might have had a 0 instead of an O or something. Anyway, I just copied and pasted to correct that. Okay, now let's set up our measurement. Down here in Project tab, I click Graphs, I right-click, click on New Graph, Rectangular, Create, right-click, Add New Measurement. The measurement type is fine. Measurement type is System, WVFM, Default is Time Domain Waveform, everything's perfect. Block diagram's good. Test point, let's do the output. And microseconds, time span, let's make this thing 40. Take off, wait for full window. Right click, add new measurement. Set our next test point. This will be our input. Leave everything else the same. Click on this little box and make this our next test point. Hit apply. Click on this legend and we're going to change it. So go to measurements tab. Instead of use default, go output. Apply. Next. Input, apply, next. Air, apply, go to traces, blue curve. Let's change the weight to make it a little thicker. You can change the colors if you want. You can change this to green. The air signal kind of makes sense to be red, so I'll change that to red. The weight, change that, hit apply. We're not quite ready yet. We need to set the sampling frequency now. So go to options, default system options, simulator. Let's stop our simulation after 15 microseconds. So right now it's in nanoseconds. Let's hit cancel. We need to set the units. Options, project options. Global units, time to microseconds. Okay. Options, default system options. Stop the simulation after 15 microseconds. Let's data rate, let's make 100 megahertz, and oversampling is 1. So VSS is a sampled time domain simulator, and you have to have a sampling frequency. Our input frequency is 1 megahertz, so we're going to vastly oversample. So our sampling frequency is 100 times our input frequency. And that way, when we look at the graphs, they'll appear to be continuous time waveforms. You're not going to see the discretization due to a low sampling rate. Hit OK. Save. PLL. Yes. Cross our fingers that this thing will work and hit run stop simulation, and it does. The screen is kind of hard to see, and I double click. Let's make this. We'll make this brown, and we'll go a little there. Okay, so what you're actually seeing is the phase lock loop doing exactly what it needs to do. It's locking to a specific phase. Now the input frequency is 1 megahertz, and the free-running frequency of the VCO is 1 megahertz. The input and the output signals are in phase when you first turn the system on. When it's ramping up, you can see the blue curve and the brown curve are their minimum happens at the same time point. But what happens is later and later as you go on, now like 8 microseconds later, the blue curve is leading the brown trace. So the blue curve is the output and this brown curve is the input. So the output is leading the input And it turns out it's by 90 degrees because of the multiplier type phase detector we're using. This red curve is the error signal. Now there's some transient that's happening. So some signal is being fed into the VCO, which is increasing the frequency a little bit. So it's accumulating some phase. And then there's this little oscillation, and then the error goes to 0 when this thing is locked. So when this error is 0, the blue curve is leading, or should I say the output is leading the input by 90 degrees. Let's now click on this. And I want to see how this curve changes when I change, I don't know, let's change the cutoff frequency. So we're going to set the cutoff frequency of our low-pass filter to be a variable and look at different values of the cutoff frequency and see how that changes the loop dynamics. So that's what I just did. I clicked on this tuner tool and then clicked to say, hey, that's a variable. I go back to my graph, click on tune, and here it is. Now, nom is the value it is right now, so it's 0.5 e to the 6 or 0.5 megahertz. Max is the maximum value that this thing can be set at. I don't know, let's set this to be 2 e to the 6. So you can also tune this with a slider if you want. So you can find the value between a max and a min. Min, I'll just make 0.1 e to the 6. Okay, so now let's lower, actually let's increase the cutoff frequency so that we're letting higher and higher frequencies in. See what happens there. So kind of look at this curve. I'm going to increase the cutoff frequency and then we'll see how everything changes. So I'll change it to 0.7 e to the 6. 0.7 megahertz. Okay, what happened is it reached steady state faster, so that the system responded faster. This red curve is the error, and before it kind of took some more time to reach steady state, and this time it took less than 4 microseconds. But what you pay, the price you pay for a faster lock time are these oscillations in the air. These oscillations in the air are going to translate to phase noise. Phase noise means that the output tone isn't pure. Here's our reference again. The output tone is going to look more like this. So ideally, you would have this perfect single tone with one frequency at the output. But when that air is oscillating, it's going to kind of spread this signal in frequency and kind of degrade the spectral purity of that signal. So you have some phase noise, basically. Click on this to see. So that's what happens when you increase the cutoff frequency of the low-pass filter. Now let's decrease it. So I'm going to click up here on my tune tool. I'm going to decrease it to, let's go pretty low, 0.2 e to the 6. 0.3 e to the 6, 0.3 megahertz. Now what you're going to see is the transient's going to take longer for this thing to lock. See, it doesn't even lock. We're at 15 microseconds. It's barely, it's not quite locked there. So to change this time, I'm going to go to Options, Default System Options. Let's stop after 25 microseconds. So this thing is finally locked at around 25 microseconds. So it took a lot longer, but what you benefit is that this red curve, the air curve, is going to have less oscillations. It really even hasn't converged just quite yet, has it? Let's go to Options. Well, let's make this a little bit longer. Take a bit. So I just set the simulation time to be 35 microseconds. And way out here, that the air signal is finally converged. You don't see those oscillations, so you'll have a higher, or the output tone will be, will have less phase noise. And again, when this thing is locked, the blue curve, which is again the output, will be locked in phase to the input curve, and will be basically the output will lead the input by 90 degrees. Okay, so let's change our cutoff frequency back to 0.5 e to the 6. That's a pretty good value. So options, default system options, let's go back to 15 microseconds and click this button to see everything. All right, so we're kind of back to where we began. Now, I want to lock to, right now, when this phase lock loop is starting up, the phase of the input is equal to the phase of this VCO, and eventually the VCO will lead the input by 90 degrees. Let's make sure that this thing will lock if the inputs are different in phase. So I'm going to make the input phase a variable, and I'll take off the cutoff frequency of the low pass filter. So now we're going to change the phase of the reference signal and make sure we can still get a lock. So now I hit tune. Max phase I want to deal with is about pi 3.14. The minimum is negative 3.14. Everything looks good. Let's make sure it's the same. Okay, good. Hit tune, and now I'm going to change the input phase difference with respect to the phase of the VCO to be 0.5. I don't know, just some number. And you can see that eventually it locks, and the blue curve is still 90 degrees, leading the ground curve to output. Let's change the phase to, I don't know, negative 3.14. Oh, so negative 1.5. And let's see how this thing changes. Ooh, it locks pretty fast there. Because what I just did is I set the blue curve to be 90 degrees, more or less, to lead 90 degrees ahead of the output. Again, when I say, excuse me, I set the output to lead 90 degrees ahead of the input. And so it didn't take long to lock it all. It was almost already at lock. It was almost already locked. So there's that. I'm going to change the phase back to 0. And then resimulate. Everything should be the same. Now, how does this change when I change the value of VCO gain? K underscore VCO. Again, that's the gain of the VCO. When I say gain, that's not like voltage gain, but it's the voltage to frequency transfer coefficient. Okay, so let's make that a variable. Click tune. That. And by the way, you can look at multiple variables. I'm just selecting one at a time to make things a little bit simpler for the video. Okay, so now I go back to graph, click on tune, and set the min to be 0.1 e to the 6. That's some room. Okay, so let's set our nominal. Let's increase K. I don't know. Right now it's at 0.5 megahertz. Let's go to 0.8 megahertz. What does that do? Maybe there's some more oscillations. Maybe the transient might take a little bit longer for this to lock. I don't really see much of an advantage right now. The advantage of increasing K happens when the input frequency is not equal to the free running frequency of the VCO. But you can see it's starting to kind of get more unstable. Let's look at what happens if you have a really large K, 2e to the 6. And when I say K, that's the letter, that's the symbol that stands for the gain of the VCO. I'm just saying K. Oh, it's still oscillating. I don't know, maybe I can't get it to resonate. We'll try one. Oh, it's the max is set. Let's change the max to 5. So I thought I clicked, 2 megahertz, but it was higher than the set max. Anyway, I had to change the max. Let's go again. Let's go to 3 megahertz for K per volt. There, you can start to see it's just unstable. The output signal is not a pure sinusoid at all. It's going all over the place in frequency and phase, and the air is oscillating. So when you increase K, you decrease the stability of this system. Or you can say you decrease the attenuation of the system. Okay. I'm going to change K back to 0.5. When I say, okay, you don't decrease, when you increase K, you decrease the, what is it called? I'm spacing on it, so I'm not going to worry about it. Damping factor, that's what it is. Okay, everything's back, set how we had it. Let's make sure, good. Now, things get interesting when the input frequency is different than the free running frequency of the VCO. So I'm going to make the input frequency a variable, and I'll make, let's look at the cutoff frequency. So we'll make these two variables. Let's see, will this lock to an input frequency that's 1.05 megahertz? Yes, it does. So what's happening now? You can see there's this transient that happens while this loop is locking to the input, and then you have this steady state error that's just like a DC value. The blue curve, the output, is indeed being locked to the frequency of the input, but it is no longer leading the input by 90 degrees. Kind of hard to tell because we're just looking at this in the time domain, but this blue curve is not leading this dark brown curve by 90 degrees. And then on top of all that, and the reason why this is happening is that we have an error signal. That red curve is right here. So the error signal is this, it's not just an error signal, but it's also being fed into the VCO as a control voltage. So it locks in frequency, but not in phase. Let's increase the input frequency from 1.05 megahertz to 1.1 megahertz. Leave everything else the same. And you can see it locks in frequency again. Now, however, the error, which gives you an idea of the phase error between the input and the output, has increased. You can see this red curve was lower before and it rose when we separated the input frequency from the free running frequency of the VCO itself. Will it track at 1.3 megahertz? Let's find that out. So now we're not getting a lock, and all I did was I increased the input frequency, or the frequency of the input signal, to 1.3 megahertz, and this system is just not locking. It's outside the capture range. Let's see if the cutoff frequency, maybe if I increase the cutoff frequency, can we capture it? Who knows, let's find out. So I'm increasing it to 1 megahertz. Nope. I'll go back to 0.5. Okay, so that's kind of the basics of how this thing locks in frequency. Let's now turn off cutoff frequency as a variable, and let's look at, again, the gain of the VCO, which I'm calling K underscore VCO, or just K, as a variable. And let's get our input frequency closer to our output, so, or to our VCO free running frequency. So I'm going back to 1.1 megahertz for input frequency. Yes, this thing locks. This thing locks. So the blue curve over here is 1.1 megahertz. It locks in frequency, but it's no longer 90 degrees leading the output trace. And here's our error. If we want to get these oscillations in the error lower, we know we can lower the cutoff frequency. What happens if we increase the gain of the VCO, K? What I'm expecting to happen is this red curve, the error, will decrease, which means you're decreasing the phase error. Right now, I just kind of click on it, and it's around 0.2. It's oscillating. It's about 0.2 is kind of the DC value. Our K is 0.5 megahertz. Let's go to 1 megahertz. So I'm doubling K. Look at this red curve and see what happens. Well, it's taking longer to lock, but I think it's going to lock, so we need to actually zoom out. So options, default system options, let's look at 30 microseconds. Eventually this thing does lock. So the blue curve, the output is eventually has the same frequency as the input, but it takes a lot longer to acquire. But if we click now, this error signal, the red curve is around, I'm looking at the second number down in this box, is about 0.1. So we have the error by increasing our gain of our VCO. So what if you keep increasing the gain of our VCO, or voltage controlled oscillator? Well, it's going to take longer and longer to lock, and at some point it's just going to go totally unstable. So let's double our VCO gain again, double K. And it's just not locking. The system has gone unstable. So I'm going to go back to options, not project options, options, default system. Let's go back to 15 microseconds. And this thing is unstable. Good. So let's lower our value of K. See if we can get a lock again. Let's lower it one more time. 0.5 megahertz. Okay. Let's see what happens when we lower K too much. Let's lower it to 0.1 megahertz. If K is lowered too much, you kind of get this characteristic signal. I can keep simulating on, but it's never going to lock. In the end, what happens is when the gain of the VCO is too small, you don't get enough DC voltage to drive the VCO towards lock. If you want to learn more about that, that's all in this paper. What is it? I mean, I think this paper is just excellent. I think I went too far. You kind of get these, it's kind of trying to get lock, and it's not acquiring a signal. And here's an actual simulation. And we're kind of seeing that. I'll simulate a little bit longer. So options, default system options, let's go to 30. You get this attempt to lock, but the gain is just too small for this thing to lock correctly. So there's a sweet spot. You don't want K to be too small. You don't want K to be too large, right? Let's go to 0.5 e to the 6. Let's see if we get a lock. Oh, something funny is going on. Let's stop it. Options, default system options. Let's stop the simulation after 20 microseconds. Okay, so I changed K back to 0.5 megahertz. What happens now? I'm going to increase the frequency, the input frequency from 1.1 to 1.2 megahertz. Do we still get a lock? So we don't get a lock. We're outside the capture range. So there's a certain range of frequencies with which a phase lock loop can lock to, or at least its basic implementation. And everything is with respect to the free running frequency of the VCO itself. And what I'm changing is the input frequency to 1.2. That's 0.2 megahertz greater than the free running frequency of the VCO, which we set to be 1 megahertz. Let's increase K to 1e to the 6, 1 megahertz. So if I increase K, I get a capture again. But of course, there's a limit to how much you can increase K. Again, K being the gain of the VCO. All right, so that's kind of the basics. You can play with this phase lock loop stuff all day and really just pretty interesting. Okay, I'm going to change the input frequency back. Let's go to 1.1 e to the 6. Let's leave the cutoff frequency as it is, and let's change the VCO gain to 1 e to the 6, which it is. That's great. Make sure. Again, here's our graph. The problem with this circuit is that it will lock in frequency but not in phase. That error is not at 0, which means you have a phase error between the output and the input. Sometimes you actually, in many cases, you want to lock not just frequency but phase. So how can you do that? What can we add to this thing to make this go from a type 1 phase lock loop to a type 2? We're going to add a PI controller. Capital P, capital I, if you want to look it up. PI controller is used in control theory, and we're going to use them right here in our phase lock loop. And it's basically going to model a charge pump, and it also models an integrator that you can construct with an op amp. And there's a few components to this. So I'm going to go to signal processing. We need a couple gain blocks. Here's my gain block. Over. We need a summer, math, and we're going to need an integrator. PI controllers, integrators. So we're going to put an integrator right there. There we go. And adding all this stuff is going to give us a big advantage. Let's see. Click on these arrows, and I got it set to real data. Zoom in. Of course, right there. Okay, we got to set the gains correctly. Well, I already designed this, so you know that they should be these values. The purpose here isn't to show the design of all the gains and all these blocks, but just to, again, explore the properties of phase lock loop. So we're good there. We're going to, yes, look here. This is the error. This is what's coming out of the phase detector. And I'm going to go to options, again, default system options, and let's set this. I know it's going to take a bit longer to lock, so 35 microseconds. Graphs, and let's see if this thing achieves lock. Usually this simulates a lot faster, but because I have this video capture going on, it's taking a bit longer. There we go. So I'm seeing that it pretty much locks before 20 microseconds. I'm going to pause it and go back and change it. We don't need the whole 35. Okay. Now at first glance, this might look very similar to the behavior of the phase lock loop before we put this PI controller, but there's a very big difference, very important difference. And before I say that, let's just do one quick overview. What's going on? Here's our input signal. It has a frequency of 1.1 megahertz. This is our phase detector, a multiplier and a low-pass filter, and the cutoff frequency of the low-pass filter is set to be 0.5 megahertz. This then goes to a PI controller, which has an integrator and 2 gain blocks and an adder. So think of this as just another filter. It's linear. And then this goes into our voltage controlled oscillator, which has a free running frequency of 1 megahertz, an output power that's set to 6 dBm, and it has a gain in voltage per hertz, volts per hertz, that is denoted K underscore VCO. That is 1 megahertz per volt. And we're looking at the output. We want this to be a sinusoidal waveform, a tone, that's locked in phase and frequency to our input. We're looking at the output, the input, and our error signal. When this signal is 0, that means this and this are locked in phase. That means that this is actually leading, when I say this, I mean the output is leading the input by 90 degrees, and that would make the error 0. The red curve is the error, and look, it goes to 0. The blue curve is the output, and look, it's not just tracking the frequency of the input, but it's also tracking the phase. There's a fixed phase relationship. It's leading the output by 90 degrees. See that? It takes the trade-off of using this filter is that it takes a bit longer for this thing to acquire lock. Let's see what happens if I increase the input frequency to 1.2 megahertz. So it acquires lock at about 15 microseconds. But when it acquires lock, the error is 0. The output of the VCO is locked to the frequency and phase of the input, as you can see right here when the error goes to 0.